language. Most of the lecture will simply be here inside Eclipse. I'm starting this off where the last kind of live lecture ended, where we're moving around the camera and doing stuff. So I'm just gonna start it at code that you can see where I get to, started from scratch. It means we're gonna have to program a fair bit into the shader language, but I'm gonna I'm gonna allow us kind of 2 lectures for this, so I don't have to hurry too much programming. If we manage to get through most of it today, then okay. If not, we'll just continue Tuesday on the same material. However, I want to begin, before we go into Eclipse, just a little bit on an overview of the shaders themselves and how they work in the pipeline, and kind of what the things are here that we're sending in, what these variables are, what these values are, and how they're used both inside the OpenGL pipeline and also how we kind of send the values into the pipeline from our own program code. So I'm going to start drawing an image here. I hope it'll end up fairly clear, but I'm going to start by kind of splitting it into 2 parts here. One of them is, well, split it into 2 parts here. I'm going to see if I can't. So this would be the OpenGL pipeline, and I'd very much like this to be a little bit bigger. So we have the OpenGL pipeline here, and we have our own code. In our case, it's Java code, through libgdx, so on and so forth. But we could be doing this in C++ or Python or whatever programming language. And we're kind of going to look at what we're sending between here. So in the pipeline, we have the vertex shader. See how quickly I can do all of this here. Vertex shader. And we have a bunch of, in the vertex shader, we have variables such as attribute, we have uniform. These are the variables that we've been using so far. We have something called varying, and in later versions of OpenGL, these are often called in and out rather than varying. I'm going to stick to the varying name, but I'll explain how this works. In some cases, you'll see that this is being deprecated or is somehow an old naming convention, but in some cases, you'll have a version that doesn't understand the other naming convention. So I'm going to stick to varying because that's going to work. But for future reference, in some cases, this is called in and out variables. All right, so attribute is basically our vertex lists. Uniform is just variables that we change ever. And varying has to do with vertex versus fragment shaders. All right, so this is our vertex shader here. Let me see if I can. Okay, fine. And then we have our own code here. So the vertex shader itself is otherwise just a program, and it has this C-style code. Why did this suddenly become tiny? So the vertex shader is simply a program that is run. The variables are just variables that are defined before this main function in the program. So we have a program, and it's simply a main function. But before the main function is defined or is implemented, there are these variables. So whenever the vertex shader is run, we simply run the main function, or OpenGL runs the main function with whatever values are on all these different variables. These uniform variables, attribute variables, and varying variables. We'll see this better when we start doing it in the program. So in our own code, things that we can do is we can set values to these uniform variables. But in order to set the values to it, we have some value here. Value. All right, so we have a value that we want to send into a uniform variable. Before we can start sending variables, we kind of need to get a handle. Sorry about this. So we need to get a handle to this variable. So what we do is we compile the shader program. Once we've compiled the shader program, all these uniform variables will have certain IDs. Then we can call certain functions to get a handle to that. So basically get an integer, and that integer tells us this is simply an ID of a particular variable in our shader. And then at any given point, after we get this handle here, we can say we have this handle. Then we can, in our own program, take a value, send it along with this handle to OpenGL, and OpenGL will make sure that that's the value that's put into this particular variable. This image may not be showing it clearly. I'm trying to show the idea. In the code later, we'll see exactly what we're doing with this. So there are a few steps that need to be taken every time basically we introduce a new variable into a shader. We have to make sure that our program is getting the handle for that variable and storing it somewhere. So every time we want to put new stuff into that variable, we're going to be using that handle. Attributes, however, as we've discussed in class a few times, the idea there is not that we don't set values to the attribute variables. Instead, we have value lists, lists of vertices, lists of normals and positions, lists of colors, all kinds of things that we want to say OpenGL should take this list, and then it should just start the list, go at the top space of the list, the first vertex, and set the values from there into this attribute variable. Then it runs the main program. Then after it's run the main program, it'll simply go to the next set of values in the list, send those into the same attribute variable, and then run the main program again. So the attribute values are set when we're actually running the main program, whereas the uniform variables can be set at any time we want. And after we set a uniform variable, that is going to be the value on that variable indefinitely until we simply set another value to it. So we set a value to it, that's going to be the value of that uniform variable until we set another value, or until the program stops running, or whatever. Whereas the attributes, it's when we actually start running the pipeline. We say, I have a list of values here. It may be several lists, actually. A list of positions, a list of normals, different lists. And I say, I'm going to set the shader vertex pointer, basically set the vertex pointer of OpenGL and say, this is the list of vertices that you're supposed to be reading from now. However, we also still need that handle. That is, we get a handle to the attribute, so we can say, here is the list that you should be reading into the attribute variable with this handle into. And here is another list, and there's another attribute variable. This list should be used for that variable. Once we've set this up, we simply tell OpenGL, start at a certain position in the lists and draw a certain number of vertices. When we do draw arrays, or draw lists, actually, which is another function that we've discussed a little bit. And OpenGL will simply go into that list. It'll start at the top, and it'll take the corresponding values, send them into the variables, and run the main loop. So that's when we actually run the OpenGL pipeline. All right. So to begin with, let's look a little bit at this in the code. Are there questions regarding these ideas? Okay, so let's look a little bit into our core program here. We have these assets here, and we have these shader files. Before we look into them, let's start by simply opening our, where do we have game program here? Here we have a few variables in here, like rendering program ID and vertex shader ID and fragment shader ID. These are handles as well that OpenGL sends us. That is, the values that will be in those variables will be handles that OpenGL gives us. But these are handles to the actual shader programs and the linked program itself. Then we have all these that my naming scheme basically ends with LOC on them all, which basically means location, sort of. But these are these handles. This is a handle to a variable that's called position in the shader, a handle to the normal in the shader, a handle to a variable that holds the model matrix, view matrix, projection matrix. So these are all just integers, but what these integers link us to is actual variables in the shaders. Then we have here color location, and in our simple shader that we have now, then that's basically everything we have. If we look at a little bit of the OpenGL shader functions here, or operations that we're calling. To begin with, we basically take these strings here, vertex shader string and fragment shader string, and we simply read from these files. So the first thing we do, and we can take the vertex shader here and look at it. So this is the entire thing. This is the entire shader. And it's just a program. We have some variables. This is the type of variable, vec3. We have, it simply means a three-dimensional vector. Matrix 4, it means a 4x4 matrix. Vector 4 means it's simply 4 floating point numbers. So we have uColor. So these are all our uniform variables. We have these attribute variables, which are the position and normal. Those will be sent in from the lists as we run the program. And then we have one varying variable, and I'm going to look at that a little bit later. So we set these things, as we've already looked at, setting the matrices, setting the color, and then this is the main program that's run. So this is simply read as a string into these strings here. And after we have these, we call this GL shader source here. And we say we're going to put this string, this is our program string, our program code. And we want to link that program code to this shader ID. Or before we did that, we actually called create shader. So we create a shader, and we send in this constant vertex shader to tell OpenGL we're going to create a vertex shader program. And we're going to create a fragment shader program. And OpenGL simply creates this internally, makes this program, makes room for it, sets up everything that OpenGL needs to set up. The only thing it returns to us is an integer. And this integer will be our handle to this shader from then on. So now we have IDs to a vertex shader and a fragment shader that basically have nothing in them, but are ready for us to send into them. First, the code. So we're saying, okay, we're going to send in source code for a shader. We're going to send it to this ID, and we're going to send it to this ID. Then we call GL compile shader, and then we simply send in the ID. We tell OpenGL, you have a shader ID that you've set up. I've sent some source code in there. I want you to compile this shader. This may or may not fail. So it's actually nice after we link it. Okay, I don't have it in this program. We'll add that later. We can actually get kind of the error messages from compiling the shader. Once we start compiling the shader, that's something that's very nice to have. Let's see if I can remember. Shader info log. This gives us a string. Okay. So if I take the vertex shader here, the vertex shader ID, and I say I want to call this function get shader info log, and what I'm going to do with it is I'm simply going to do system.out.println. Okay, so what I've added here, after I compile the shader, I simply write out into my console the information log about that. We'll look at later what comes out. but it can really make a difference. Let's do it for the fragment shader as well. It can really make a difference when we're making changes to the shader. If we forget a semicolon or something like that, Eclipse won't compile our shader beforehand. It's just text. We just send it into the hardware compiles it, and the hardware will send us error messages. So these error messages will actually be different, like the verbosity of these will be different just between different graphics cards and so on. So this is a compiler that's lying on our hardware. It'll compile this, and in order to get some information out of it, we can do this. All right, another create function here for OpenGL. It's a whole rendering program that is created now. So a rendering program consists of several shaders. In our case, it's going to consist just of these two shaders, the vertex shader and the fragment shader, and we're going to leave it at that for now. You can read up on different types of shaders and how they fit into this entire pipeline, but for now, the vertex shader and the fragment shader are the ones that are absolutely necessary. You can't run an OpenGL pipeline without those two, but you can run them without any of the other shaders. So again, create program, and now we get the rendering program ID. So the IDs or handles that we have, the rendering program ID is really the most important one. The vertex shader and the fragment shader IDs we never use kind of outside while we're compiling them. Once we have them compiled and once the rendering program is ready, we don't really need to check those independently. If they're compiled correctly and linked correctly, then the rendering program is something that's nice to have, because we can compile several shaders at the same time. Like in our create function, we can compile several shader programs, store different rendering program IDs, sorry, and then we can switch between them as we're programming. For instance, if we have a split screen and in one of them there's a 3D environment and the other one there's a 2D environment, like a HUD, something like that, information environment. We can have one 2-dimensional shader and another 3-dimensional one, or one optimized for certain types of lighting and another optimized for something else. One optimized for character models and another optimized for tree models. So we can switch between these shaders as we go. For now, we're just going to be working with one though. Okay, so we're here now. We've created this program. We attach shader, say this rendering program now has this vertex shader. This rendering program has this fragment shader, so we've attached this. And finally, link program. So if all of this works out correctly, if both of them compile correctly, number one, and the varying variables in both of them fit, because the varying variables are kind of a connection between the fragment shader and the vertex shader. If all of this comes out correctly, link program will be okay. Then we can continue with our OpenGL program. All right. You can also see here that when I start getting these locations or these handles to different variables, just take the color location here, I'm telling it that in the rendering program, linked to rendering program ID, there is a variable called u_color. And you can see that I'm not referring specifically to the vertex shader or the fragment shader. I'm referring to the rendering program as a whole. So we can't basically use the same variable name in the vertex shader and in the fragment shader unless they actually mean the same thing and they are the same variable. So I'm saying there's a variable called u_color, and it's linked to this rendering program ID. And I want the handle for that. I want an integer that I can use to send information into that. So all of these here, simply tell OpenGL, give me an integer that I can use to talk to a certain variable. And then this I added. I don't really need it at this point because, you know, it's the only program that's there. But this is what we would use in order to switch between programs. If we've compiled several programs, we have links to all the different variables, we have all this set up. Anytime in our program, the only thing we need to do is call GL_use program with the correct rendering program ID, and then we've switched to that particular set of shaders. Other questions regarding this idea of just setting up the shader, linking to the variables? And if we look at the color again, this is the function that we use. Oops. Sorry, this is the function that we use to set values to that variable. So only once when we're creating this do we need to call this. Then we have this integer here that we can use to link it. This integer I use as an ID here, so I'm saying GL uniform 4F just means 4 floating point values, but there's, sorry, GL uniform 3F and GL uniform 2F and GL uniform FV for floating point vector, so on and so forth. A lot of different versions of GL uniform. In this case, however, GL uniform 4F simply says, first you need to tell me what variable it is that you want to set values to, then you simply send in all the values. In this case, it's 4 floating point values, red, green, blue, and alpha. So, okay, that's kind of the base that we need to know about using the shader language. Other questions regarding this? Does this seem clear? Does it seem like sane programming? It's kind of what we need to do to link together two seemingly different programs. We have our own code, and then we have this C-style shader program, which is kind of a different program altogether. And what we need to remember is that our own code, the Java code, is compiled on our computer until it's a running program and we run it. This code here isn't compiled when we compile our program. It's compiled when we basically send it into OpenGL in the beginning of the program. So the compile time for this program is during runtime in our Java program, which means that in order to get errors in the compilation of this program, we kind of just need to read them from the console of our running Java program. All right, I'm going to see if, oh, I'm wondering if we can open this, open with system editor, do no, open with text editor. Okay, fine, then we get it at least here. Okay, it's nicer to read this program. Is this too small for you to read? Do you want it bigger or? Cool. Yes, we can do that. So yeah, this is a program. It's fairly simple. We've gone through what it does before, but let's just kind of step by step through this again. This is what's happening in the vertex shader. We take this position. This is more just kind of taking this vec3 here and making a vec4 out of it in order to be able to use the matrix multiplications. So we're taking the x, y, and z coordinates and adding a 1. This can be done differently. You could already take in vec4. You can do all kinds of things. However, since this is a point, we put a 1 here. Since the normal is a vector, we put a 0. Then both of them are simply multiplied with the model matrix. And then we get the current position. Then we take them both and multiply them through the view matrix. What we're going to change with this, though, is that we're going to take the color calculations or the lighting calculations and we're going to move them into global coordinates. That is only after multiplying with the model matrix. Which means that since the normal is used during lighting calculations, we're not going to need to take the normal through the view matrix as well. We'll explain what's happening here. This is a very, very simplified version of diffuse lighting. Can you see what it's doing here? Can you just look at this line and realize what it's doing? Like if we write this up, what do lighting calculations look like to begin with? So something equals, and we're doing something dot something. So it was n dot something. It wasn't really an up vector that was there. It was a particular vector. What do we usually do? We say there was this vector s, which was pointing from the position to the light. Okay, so we have our position P here somewhere. Here we have the light, and we have this vector S. That's what we usually do, right? And then we divide it by the length of n, and we divide it by the length of S. And this was Lambert, right? Except we said if it's negative, then it ends up being 0. So there was a max 0, so on and so forth. So if we compare that to what's happening here, we're doing a dot product of the normal and 0, 0, 1. And then we're dividing that by the length of the normal. Why are we not dividing by the length of S?
Because it's 1.
Okay, the length of this particular S that we're using is 1. Okay, so we basically don't need that. And we're not using S. We're using what? 0, 0,
1, 0.
1. And the 0 was kind of just to say that it's a vector. And divided by this times the length of that, which is 1. How can we use this vector and say that this is somehow a representation of the vector towards the light? What happens if I draw this image up? If we say, okay, let's say this is my y-axis, this is my z-axis. This is when I'm kind of doing projection. I'm in I-coordinates, so I've put my camera kind of down here in the center of the universe. So I'm basically saying whatever point I have, here, here, or here, I'm always using the same vector as the vector to the light, which is the vector 0, 0, 1. So I'm basically doing a very crude simulation of the light being behind the camera, because I'm going into I-coordinates before I calculate this, and then I just always use the vector 0, 0, 1 as S. So that's the idea. That's what this particular shader is doing. It's simply, and then it multiplies that with a color, so that the color that we put on the material will actually make a difference. So if we look at what this looks like, you can see that when I'm looking like to this direction, this part here is really dark, this one is bright. When I move the camera around, suddenly this one is bright. So the light is kind of moving with the camera. Another thing you'll see as well, though, is that just by turning the camera, I'm actually affecting the light, because it's always the same vector, and this vector is linked to the direction of the camera. It's kind of the light is not coming from the camera as such, it's coming in the same direction as the camera is facing. Okay, so this is the shader that we have now, a shader that kind of simulates this very crude light coming sort of from the camera. What's good about this is that we can set up a scene and we can walk all around it and we'll never be in darkness. We always have light kind of with us. But it's not a very good representation of the position of the light. But I think it works to actually see that our environment is actually three-dimensional and it's working and that everything's in the right place. So then the question is, let's say that at this point, we want to implement better lighting. Let's make that be the first thing that we do in order to kind of learn to use the OpenGL shader language to make some changes. Where would we start? Like at which end would you feel comfortable starting? If I want to put better lighting calculations in, would I start at the shader? Would I start at the other end in my Java program? Like, where do we work this? Like, where are we going to have to make changes? For instance, now we only have this color. And when we're looking at lighting calculations, we know we need the light diffuse intensity and the material diffuse intensity and material specular intensity and material ambient. All of this we kind of need. So we're going to need to change our variables, right? So let's make it simple to begin with. But let's at least go in here and say, okay, we're not using color anymore. We're using material diffuse. Okay, let's start with that. What more do we need to do lighting calculations? even if we're going to do a simplified light and say just the light is always just one color. We don't need separate diffuse light and specular light and ambient light for the light. We're just going to use one light color, and we'll use that for all those calculations. The material, though, needs to have separate diffuse and specular and ambient, because otherwise, there would be no difference. So we're okay with the light just being one color, but we want the material to be kind of complex, so we can make one matte surface and another shiny surface and so on and so forth. So what do we need more than just material diffuse?
Material spec.
Okay, material specular. Let's wait a little bit with that, because what I like to do in this as well, especially in shader programming, is just do little bits at a time, make them work, and then add to that so we don't put too many variables in. But what variable will be absolutely necessary just to do diffuse lighting?
Lambert.
We're going to need to calculate Lambert, yes. So something about the light. And Lambert, as we looked at it, it used N and then it used S. Let's go back to that here. So in order to calculate S, what do we need? We can either send in S as a direction, or we can send in a position of the light that we can then calculate S from. So we're going to need some light position, all right? So if we go in here, we're going to need a light position, right? What more do we need about the light? Some kind of color value for it. So we could say light diffuse and then light specular and so on and so forth. I'm just going to go ahead and do light color. That's the intensity for the light that we're going to use. Okay, so we have the light position, which will give us S. We have the material diffuse color and the material light color. So the calculations, the entire calculations for diffuse, where we have Lambert here, and then we had something, 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 then plus Lambert times our intensity for this light in red or something like that. And then we had the value for the material in red. Okay, so now we have this. We have a color for the light. We have a color for the material diffuse. Okay, we had material diffuse, red, and blah, blah, blah. All right, so we have these things. Should we do the calculations in here now? I guess we might as well. But what do we expect to see once we run this program now? Okay, for some reason it crashed. So if we look into the console now,
you no longer have U color.
Yeah, okay, so version blah, blah, blah. To begin with, U color undeclared identifier. So it's telling me in line 33 of my shader program, I'm using the variable U color, but that variable isn't there. Okay, so already the compiler, the C compiler on my graphics hardware is giving me information about what's going on. Assign can't convert from float to varying 4-component vector of float. All right, we can get this. So what's happened here is that the lines that I added here earlier are coming into play. The get shader info log, particularly for the vertex shader. So we're going to have to add something to this program. However, let's start by just getting the shader itself right. I think it's usually best to get the shader itself right until it compiles with as little of changes as we can get away with, and then just do more changes later. So what are we going to do here? We are, to begin with, like I already said, we're going to do our calculations in global coordinates because we feel more at home there. Doing things in I coordinates can get tricky, especially defining positions in I coordinates. Okay, so in the end, we're going to do V color equals something. So this is a nice formula, except we want some vector S here. And we want to the length of the normal times the length of S, right?
No. Time, yeah, we don't.
Except we want to put this into parentheses here, so we multiply those together and divide by both of them. So how do we find S to begin with?
Light position minus position, or U position.
Okay, so vec4 S, so we're going to make a new vec4 here, equals light position. This is one thing that people sometimes get frustrated with. You get no code completion or anything. We're just writing this like a text file. Light position on a times minus
A position.
yeah, or not a position actually, because a position is the original position that came in its own local coordinates.
So then
We're in global coordinates. Yeah, this position here is what we've already taken through the model matrix. So this is the position that we're looking for. Now we have S. I would like to go ahead here and say I'm going to make a float called Lambert, just to make this nice and clear. Equals this. Except, is this exactly Lambert, or do we need something more? We might get negative numbers from this. We're not interested in those.
The max of that is 0.
Yeah. We do a max of 0 and this, and I'm pretty sure that max is a, the word Lambert is not correctly spelled. I beg to differ. Okay, so U color we don't have anymore. So what's our color going to be now? Given that we're only using one light and we're only using diffuse calculations, no specular.
Lambert
Times
light color times material diffuse.
Yeah, material diffuse. Now here's one thing about the OpenGL shader language that is specifically designed for exactly this. And that is that if I take a vector and I multiply it with another vector, this is something that in conventional math isn't allowed in general. You don't take a vector and multiply it with a vector, or else if one of them is a column matrix and the other one is a line matrix, they'll end up giving you a single number, which is the dot product, incidentally. So this is not going to give us the dot product. This multiplication is actually going to take each component. It's going to do a component-wise multiplication. So this will give us a new vector where the first component is the multiplication of the first components from the original vector. So the red values will be multiplied and put into a red value of the new, of the result. The green values are going to be multiplied together and put into the green value of the result, the blue values. So this is specific for graphics programming. In general, linear algebra and mathematics, taking two vectors and multiplying them together is just not defined. So we allow ourselves to do this because otherwise we'd have to do every single calculation like this in 3 lines, one for red, one for green, one for blue. So the shader language allows us to do this. So we take a color and a value and scale it. V color here is this varying variable V color. Again, this is just a vec4 color. Let's leave it at that for now. Do we need to do anything more? So we've set this V color. And what varying means, this is an input-output variable. So this is an output variable from the vertex shader and an input variable in the fragment shader. So this is enough, just set this value. We don't need to return anything in the shader. There's one thing that's absolutely necessary to do in the vertex shader, and that is to set the value GL position. We didn't define it. It's a globally defined variable. And it's a globally defined variable that the OpenGL pipeline will not continue if you don't set a value to it. So this is basically clip coordinates. So GL position, oops, is clip coordinates. Basically, GL position will have a value between -1 and 1 in all coordinates if it ends up inside the screen. If it's outside that, it'll be clipped. This is that variable. And so OpenGL expects us to use the view matrix and the projection matrix in this way. So we multiply it with the view matrix, we end up multiplying it with the projection matrix, we get clip coordinates, set them into GL position. Then we've done everything that is necessary to do in our shader, but we add one thing, this output variable that we add, vColor, we set a value to that as well. So let's, to begin with, see if this runs. It'll probably crash. But what I want to see is, okay, light position undeclared identifier. I forgot the U, didn't I? So U underscore light position. Probably going to crash again. At least it's not going to do anything. Okay, assign implicit type conversion allowed. Okay, this is a warning, version directive missing. Okay, there could be a line up here telling us the version of OpenGL. Usually leave that empty and just allow kind of each and everyone's hardware to choose their preferred version, but in some cases the hardware will complain about that. Let's talk about that later. For now, this is just a warning, no version. And this is line 30. What is happening? Assign implicit type conversion. I wonder if it has to do with float versus double or something like that. Oh, okay. So that makes it worse. So let's stick to float and leave it there. Not worry about the warning for now. Okay, so this runs, but obviously, okay, so now we have a shader that's running, but what's now wrong with our entire program?
So we haven't set material diffuse, light position, light color.
Yeah, we haven't set any of these. And also, if we go in here, we can see that we're trying to set something called U underscore color, and that doesn't exist anymore. So, okay, now that we have our shader compiling and running, we need to make sure that the variables that are there are actually the variables that we set. If we made new variables, we need to make new handles to those. If we took variables out, we have to erase the handles for those, so on and so forth. Let's take a 5-minute break, and then we'll continue with that and get this lighting calculation running.
Could you roll up the logging or the
I think it's in there somewhere. Can someone check Canvas and make sure that this is live and the video is working?
I can.
Thanks. Thank you. Are you still reading from the screen, or can I? I usually do this just so that whoever's watching the video can skip the break. It's easier to skip the break if that image is up the entire time.
The type conversion because you set a max of 0 or the optimal number, but it wants 0.0 because it takes 0 as an integer.
Thank you. Good call.
0 isn't
Can't
0.
talk just yet. No, 0 isn't 0. Even Java doesn't complain about that though. 0 is just 0. And an integer can be a float as well. It only complains if you forget the f when you put it into a float value. A double and a float can be the same, but an integer can always be put into either. However, the OpenGL shader language obviously complains about this. So we would do 0.0. And the f that we're constantly doing in Java, that's just a Java thing. That's not applicable in the shader language. So if you put an f here, it'll just complain about wrong syntax.
Yep, there you go.
So now we just have the version directives missing. And I'm going to leave them missing for now, because all of you have different versions on your computers and stuff. So to do the version directive correctly, you're going to have to, you're kind of limiting who can use it, or you're going to have to put these kind of if-def sentence and stuff around it to make sure that you have the right things going on. And this is completely unnecessary as well, especially when we're using this mainly on the desktop. Let's see if I can do this open with text editor as well. I can take this out. The reason I was adding this was if you have the same shader and you're compiling it sometimes on a phone, like an Android device, and sometimes on the desktop, it'll be GLES when it's on the phone, but regular GL when it's on the desktop. And just some graphics hardware on the phones couldn't handle high precision floating points and needed a different precision. So this can make a difference and matter when we're working with handheld devices and other types of things. But if we just want to keep it simple, then this is nice, and we have the version directive missing, and I'm going to leave that missing. All right, so we had done our vertex shader here, and we want to imagine that it's going to work nicely, but we'll see exactly what happens once we continue. But we need to make sure that our program actually talks to this program, this shader program. So we know that uColor isn't doing anything. So the first thing that we can do is we can go ahead and we can say, let's make these handle variables for all the stuff that we added and take it out for what we threw away. So color isn't there anymore. However, we have material diffuse. I'm making very long variable names here just to make sure that everything is clear. But you know, matte diff block would be fine and very understandable to anyone who kind of works in this, has experience in graphics. Material diffuse location, we have light position. Just take that separately here. We have the material here, we have the light here, and we also have light color. And again, we're not going to have light diffuse, light specular, light ambient. That's a fine lighting model as well, but we're going to make a simplified lighting model here. We're just always use the same light color, but we have diffuse and specular and ambient for the material. Okay, so now we have these three variables. Now we can go down here and say, let's just copy this line. Let's just steal this line here. Make 3 of these. I've done this quicker, but so if we want to do copy paste, just in order to make sure that we have everything exactly the way it is here, we have u_material diffuse. So this is simply the name from the shader program. So here it's just exactly the name that we have in the shader program. That's the name we use to link. OpenGL will then give us an integer that we can use to have a handle to it from then on. Light position. And light color. So another thing we need now is to actually set these values. And at this point, I would advise that you seriously think about making something like a class called shader and abstracting all of these things to there so that you can have functions there that are just called set light position, set light color, set material, diffuse, so on and so forth. Just have these little functions so that everywhere else in your code, you have this nice line that something like shader.set material diffuse, and then just 2 numbers, so that things like this, and sometimes this will become more complicated, are just there in the shader program, in the shader class. If we have time, I might do that. Probably not until next lecture, but we'll continue with this then, and then we might actually abstract this into a shader file and make more complex things. As soon as we start making this more complex, it's nice to kind of abstract things into simple functions, and then all of this stuff, all of this shader handling stuff will just be there in the constructor or some kind of initialization function for that shader, and not in our main game code here. So our game class should become gradually simpler and simpler, whereas other classes will take all the necessary stuff. However, for now, I'm gonna stick to this. So let's copy this. and comment it out and just say, we don't need to do this in the create function. Let's instead go ahead and do this in display, because very likely we're going to have scenes that are more complex than such that we can just set these values once in create and then leave them forever. For instance, here we're setting color location anyway. Okay, we have this function here anyway, so let's just grab the material diffuse, say whatever we were doing for color before, and just do for material diffuse instead now. That's the only place that this was being set.
I think so.
Okay, so to begin with, we can use a different object. We can set these to different values. All of these. Come here and make it yellow. All right, so now we're setting the material diffuse differently for each object. Again, we'd like to abstract this into a class as well and say, okay, we have this nice class that's called planet or orbital object or something like that. And that knows how to go to its orbit and transform and scale and put the correct color, so that we don't have these massive kind of blocks of code all over the place in here. Instead, we have them in one place and just send variables in. All right, what else do we need? We need to, let's just do that to begin with. Uniform 4F for light position. Oh, that was position. And then we had for light color. So let's just set light color to begin with to 1,
It's white.
1, 1, which is white. That's another thing we can actually, if we look at this original line in the shader, did I throw that out? Okay. That it didn't really have any color for the light. It just had the color of the material, and then it had the fake Lambert, and it just skipped the color for the light entirely. If we were to do that now, it would just take the light color out. It would just work like a white light, because then there's nothing attenuating it, because that would work the same way as multiplying all of the values with 1. It would not change them. So a white light, in fact, is kind of a neutral light. It's something that doesn't change anything else. As soon as we take the light down in any value, we start having an effect. But leave this at 1. We need to put a light position. What could we put in here to keep the behavior very similar to what it was earlier? So remember, we're using light position in global coordinates. So we're kind of setting those in global coordinates. They don't have their own model matrix. So earlier we were setting them in I coordinates and just using this fixed vector that was kind of pointing towards the camera. So in global coordinates, what value could we use for light position? Camera I. Okay, so if we have a camera here somewhere, right? Yep, it's called cam. So cam dot, is there not a get I? Or is this public? Dot. So we just do cam I x, y, and z.
And 1.
The 1 here is just, this is a point. We're actually not using that in our current calculations, but it would be very interesting to program the shader so that it actually checks this number. And if this number is 1, it uses it as a point. And if it uses it as a point, it does exactly what it's doing now. It takes that point and subtracts the position from it and says, now I have my vector S. However, if it found a 0 there, then we'd actually be sending a vector in for the light position, not a position as such, but a direction. Then it'd just take that direction and put it directly into S. So then we have a choice. Do we have like a light that's so distant that it doesn't really matter? If I walk 10 meters that direction, it's still kind of in the same direction, like the sun. It doesn't matter if I walk 100 meters, the sun isn't kind of moving behind me. I can't walk around the sun while I'm stuck on the earth myself. So we have the choice of just sending in a direction directly, or we can send in a position and then the direction will be calculated in this way. All right, for now, this one is one we might as well skip it. We're not using it, but let's leave it there. If you want to simplify this, I could have had this a vec3 instead of a vec4 and just skip that one. You know, I'm future-proofing somehow for more complex shaders. All right, so we have some color position, light position, some light color. We can see at least if something runs and if something happens. Okay, so the different materials definitely showing. We have green and yellow and blue and red here. The light works sort of the same in that I'm always facing the lit side. And you can see when I move around, look at this side, it gets darker when I move. Earlier, it also got darker when I just turned. That's not happening now. Because rather than this being just this general forward direction from the camera, as if the camera was endlessly wide and just shoving light from all of that plane, now it's actually in the point where the camera is. So my rotation doesn't affect it. My moving around does. Do you see other differences in the feel of this? If I watch this, you can see how this is kind of bright and it fades gradiently to here. So it goes from very bright here to less bright here. So we can see that this vertex here is getting a different value when it's being calculated as part of this polygon than this vertex and this vertex and this vertex. They each get their own. Earlier, they were kind of getting the same every time. Why? Because we were just always using that same vector as the light vector. Now we can imagine that this pointing to the camera will give a little bit of a different angle to the normal here than this pointing to the camera, so on and so forth. Like if we draw this here and we have this and I have the camera here that's also a light, we can see that the direction to here as compared to the normal, this is a very small angle, whereas direction to here compared to the normal, much bigger angle. So it's going to be a different value for each vertex. Earlier, we weren't really using this. We were using kind of the general direction to this entire plane here. So this would be the normal, and this would be the direction to the light. This would be the normal. So we always got the same value for each. So it got flatter. Now we actually have kind of this smooth gradient shading. Okay, lighting calculations are started. Let's use this chance to look a little bit at how this works. I'm not going to go into the shading itself and the rasterization. We'll do that later. But let's go up to our original image here. This. And look a little bit at varying variables. So vertex shader once per vertex. Like this here. And then I'm going to go ahead here and say this is going to be our fragment shader. Once per pixel, but not every pixel on the screen, once per pixel on the polygon. We have variables there as well. We have attribute, well, we don't have attribute variables there. We do have uniform variables there. And those are variables that we change whenever. So we also have the chance of just sticking certain values into the fragment shader. We have varying variables here. In this case, they're input variables. In this case, they're output variables. And the varying variables in the fragment shader, is autocorrect. They are weighted averages of values from vertex shader. You understand what that might mean? Basically, if we go into our program again and look at this from something like this view here, okay, we can see that this polygon is being drawn here. Let's imagine this is all one polygon when it's actually two triangles. Let's imagine it's a single quad. What happens is that the vertex shader calculates a value here, and calculates a value here, and calculates a value here, and calculates a value here. These values, for any varying variable that we make, be it color or some vector or anything we can think of, we can make a value for as a varying variable and stick it to the vertex, anything that we think we can use. In this case, the only varying variable that we're actually using is the color. So we're saying we're going to calculate a color in the vertex shader. Then we continue with the rest of the pipeline, and these colors just hang there onto the vertices. If they get clipped, we get another weighted average, kind of to, you know, we need to find new clipped point values. We need to find new clipped values for these. When this goes into the rasterization in the end, the rasterization will fill in every single pixel. So while the vertex shader is run once for each of these 4 vertices, the fragment shader will be run once for every single pixel that is drawn as part of this vertex. Not for all of these pixels in the screen, but for all of the pixels that are here in this set of polygons. So these are a lot of pixels. And the fragment shader will be run once for each. And every single time the fragment shader is run, let's say that it starts down here and it's kind of going up in lines here, always starting from the left, going to the right. It's at this point and it's going to run the fragment shader. It takes the varying variable in the fragment shader and sets a value to it that's a weighted average of this value, this value, this value, and this value, sets that to it here, and then it runs the main program. So in the vertex shader, we set values to varying variables. In the fragment shader, we need to have an exactly matching varying variable. Every varying variable that is in the vertex shader must also be in the fragment shader. In this case, it's actually the only variable. In the fragment shader, however, we can't set a value to it. We set a value to it in the vertex shader. The rasterizer sets the value to it before it runs the fragment shader. So it's an output value in the variable in the vertex shader. It's an input variable in the fragment shader. And you can see this fragment shader is super simple. GL_FRAG color is another like OpenGL internal global variable. And we have to set that. If we don't set fragment color in the fragment shader, we're not using fragment shader right. So how can we just put this here? How is this enough to get all these different values? Simply because this value that we get in here isn't the same value that we put here. We just put 4 different values in here in 4 different runs of the vertex shader. When the fragment shader is run, the value that we get here is weighted averages, like thousands of different pixels, all getting different weighted averages of those 4 values that we put in there. And in this case, because we've already done the lighting calculations in the vertex shader, we just take these weighted averages and we just say that's the color. I'm not going to do anything more here. When we start working with transparency and pixel shading or per pixel lighting and all kinds of things like that, textures and stuff, we're going to do much more in the fragment shader. But for now, we're just saying we've done our calculations in the vertex shader. OpenGL's rasterizer has done these average calculations for us. That's the color we're going to use. Whatever color we get from the weighted averages is the color that we're going to just stick in there. Are there questions regarding this? Because this is not simple as such, like this connection between. We'll go back into the image here. You can see that we have these varying variables here, they are simply kind of stuck to our kind of our vertex value. So we have a vertex here. Fingers are cold at this point, they're hardly working. So we have this vertex value here, and we basically hang a list of varying variables on it. Same with the depth value that we talked about earlier. That's just stuck in there the same as any other varying variable, except it's used internally by OpenGL rather than used in our shaders. We could actually take that and calculate it and use it ourselves and do our own depth testing if we want the depth testing to be different. So we basically hang these variables here. When it goes into the rasterization here, then it takes these values, all of these values, does these weighted averages and sticks them into the varying variables here, and then runs the fragment shader. So while the vertex shader is run 3 times for a triangle or a polygon, the fragment shader can be run thousands of times just for that single polygon, because it's run once for each and every pixel. Other questions, again, regarding this? I will talk about this more and we'll go through this. It seems like a simple idea, but then when you start kind of working with it, it gets more complicated and then simple again. I'm hoping to get us all to the point where it's kind of simple for the 3rd time and we're all just good with it. All right, so I'm actually hoping to, next lecture, get to the point where we can actually take our lighting calculations and do them in the fragment shader and truly see the difference between doing them in the vertex shader and doing them in the fragment shader. However, before we do that, let's look at how this looks and make a decision on what we want to do next. Like, what do we want to add to these lighting calculations? So we can see the colors of all this. It all seems very much, computer graphics. It all seems like these little toys. They're all made from the same matte plastic somehow. There's nothing interesting about these. We can change the colors, but we're never going to change the texture of this. And I'm not talking actual textures. We'll get to those later. But for now, just getting them to be shiny in different ways. Make some of them darker and stuff, but it'd be cool to see like the big sphere there have some kind of shine spot. Let's make it look like a yellow billiard ball. That'd be nice. So if we do specular light, that's a good idea. What do we need more now? We have light positions, we have light color.
Material, spec, material, spec.
Okay, so uniform, vec4, material, specular. Do we need more variables than this? Is there something that we need to add in order to do specular calculations?
The shine value.
Shininess. Uniform, float, shininess.
Why do you do material specular as a U and shininess just as a value?
Because I forgot the U.
Okay.
Thank you. So the U is just for me to remember which ones are uniform variables. I don't know if it's a general convention. I've seen it some places and sometimes you just know what is what. I like to use the U, so thank you for reminding me. U underscore shininess, that's a uniform variable for shininess. Okay, so those are 2 things. Anything more we need to add variables, or can we start doing the calculations now? So there was a value that we were going to calculate here. Nice often to start with this line. Okay, so it's going to be very similar to the other one, except what are the vectors that we're going to be using here? The normal and
Halfway vector.
Yeah, the halfway vector. Okay, so we need h, the halfway vector. So in order to get the halfway vector, I guess we need to calculate that. So we're going to need a vec for h. And that equals what? like what geometrical things mattered in specularity. It's how does the light shine on it and reflect into the eye or the camera. So we need a vector to the camera. Do we have that? Do we have what we need for that? So what are we going to need here?
Camera position.
We're going to need a camera position. Do we have that somewhere here? We don't really, because our view matrix is a tumbled matrix or an invert matrix. So we don't have IX, IY, and IZ anywhere in nice places. So let's just make a different, it'll make it simpler for us anyway. Just say, let's make another position here. We have a light position. Let's just add a camera position. Or I position. Or we could just call it U_I, but so now we have I position as well. So vec for B equals I position minus position. Okay, so we now have one vector to the light, we have another vector to the camera. We're going to take a halfway vector between those, and we're going to see how close is that to being exactly the normal. If that is exactly the normal, we're going to get a high shininess value. It's like the light is reflected directly about the normal into the eye, if it's further away. So here we have Fong. All right, so we can maybe simplify this a little bit, or not simplify, but just make this a little bit clearer. So let's just make all of these vectors first. U, V, H is S plus V. Is there anything that we're doing there that we could save a little time with by doing a pre-calculation here? Is there something we're doing twice that we feel is expensive and would like to do fewer times? I could normalize the normal.
Calculate the length of the normal.
Or I could calculate the length. So I want to do fewer square roots, definitely. So doing the length twice, I'm actually doing the square root twice. So let's at least do the length once and use it twice. If I normalize the vector, I'm taking that square root and I'm dividing x, y, and z into it. That's 3 divisions. And then I can skip this, but I'm doing this anyway, so I'm doing the division here anyway. So wouldn't it be nicer to just do the length and then use the length rather than actually normalize the vector? We can go back and forth on what's more optimized, but I'm thinking float and length equals the length of the normal. This might save us a little. You won't see the difference in a simple program like the one I'm doing right now, but let's do everything that we can to kind of think about, because this is something that's going to be done for every single vertex. Once we start doing per fragment lighting, that means we're going to move this into the fragment shader, so that's going to be done once per pixel per polygon. So in some cases that might be more than once per pixel in our entire screen if we have polygons overlapping and stuff like that. Anyway, so this is a little bit of an optimization. Just doing the length beforehand, but still saving the division until we've already done the dot product and made this into one number. So we just do one division rather than actually dividing into x, y, and z, and then doing the calculations. Okay, so we have Fong here. Now what do we do to the color itself?
Add Fong to the power of the shine.
Okay, so then we need Pow. Oops. Fong shininess, which is actually U_shininess.
Times U light color.
We're just using the same light color.
Times material specular.
Yeah, but we're using the material specular value. Nope. Yes.
E and A are switched.
Specular, where? Metarial. Sounds cooler. Hey, let's at least see that something is happening, but nothing is changing. Why is that?
You haven't assigned values.
I haven't assigned any values, but at least our shader is compiling, so that's good. Our code was correct. All right, similar to before, let's go up here and see what we need more. We need specularity for the material. We added
Camera position.
camera position, yeah. Let's just say here, eye position location. Did we add anything else? Shininess.
Yeah.
Shininess. Question if I was always doing material something here. It should be material shininess really, because it's part of the material. Make it everything super clear here. Although this will be a super long. We can also do something like this just to make it a little bit better readable. Right, so we have these. Now we need handles for them. So, you know, this is always a little bit of a, well, there's always a few steps here.
No, you need material.
Oh, yes.
Specular, not.
Yes, not specular diffuse, specular, and we need shininess. Here. And we need the eye position. I think this is everything we need. Now we actually need to set them to some values. So let's try one thing. Let's take this and say we're going to set specular here. Like so. Let's set it to 0. Here, here, here. Which one was the big sphere? This one probably. Yes, that's the first one. Let's put it to 1 there. Let's. Okay, this 1F. Go to shininess. Let's put 1 in shininess, just to the power of 1, just see how that looks. And since I put it here, since I set it here, it'll be there for all of them. What else do we need now?
Camera location.
Yeah. So we were actually putting the light on the camera. Now we're going to be putting the camera position there as well. I guess that's okay, but that means that the most shininess will be when we're looking exactly on the front of something. So it might be more interesting later on, to change the light position to something other than the camera. Let's at least see what happens here. Okay, something happened to the sphere. Definitely more lit. It's kind of burning out, where it has very high values on the places that are kind of facing us. And now it has also high values for that in specular. And then those values are added. So some of them actually go over 1. So it burns out there a bit. What do we expect to happen if I change the shininess? If I make the shininess 10 instead of 1, what do I expect to happen? It'll get darker. What'll happen to that big kind of circle of burn?
Smaller.
Yeah, the burn circle will kind of get smaller. So we're hoping to see a little shininess spot. Like so, but it's always kind of on the center of it. So if we make it even bigger, or even higher, the shininess value, that shine spot gets. Now what we'd like to do though, let's go ahead and set some other value for the light position than the camera eye. This is something that'll be interesting to experiment with in next class, kind of throwing the lights around, seeing how we can. However, let's just put it in a fixed place, 10. How about just 10, 10, 10, and then we can just find out where it is. It'll be very different because the light will now be in a kind of a fixed place. We can go around now, and here we just go to the dark side of this. So we're just moving a bit fast. Let's draw another sphere. Let's change the first one here, or the big cube, to sphere. Oh yeah, I already have that here. And actually have specular there be 111 as well. Okay, this is kind of weird, right? Why is it fixed there? Okay, let's skip the weird scales. Is this the first one? Let's just scale it to 1, 2, 2, 2. That's fine. 2, 2. Do you see that it's moving a little bit? The shine spot itself is moving as well, but it doesn't look super nice, does it? We can see where the polygons are. Why is this?
Because we're going off the polygon edges and not taking averages.
Yeah, or we are taking average. We can see that we have a value here in this vertex. Here we can just see this quad or these two triangles. It's simple. We have a value here, we have a value here, and a value here, and we take averages of those color values over this. Here we have two bright values, and then it goes darker, but this is completely flat. So everything that happens in between, there's no calculation going on in between. We're just gradienting it. So if we go to exactly here, we're going to get the brightest spot. Okay, we can see it's bright here, but then it just kind of, is distributed over those edges. So we're doing these averages, but we're doing the averages of a final result. What would be more interesting? Like, what is per fragment lighting? It means I'm going to do the lighting calculations in the fragment shader. Yeah, so I'm going to do the lighting calculation per pixel, but what am I going to do averages of them? Now I'm just doing the entire calculation in the vertex shader, then I do averages of the final result. I can show you this even clearer if we go back to a cube. So I'm not getting this shininess anywhere on this cube. However, if I go higher here, okay, I guess I won't be able to, maybe if I change the light position. So light position location, let's just make it 10, 0, 0, shining directly onto one of the sides. Okay, so I can go down here and look directly at this corner a little bit from below. You should be able to get a pretty strong, okay, you can see how strong it is right here. This vertex is now reflecting directly into my eye, and then it just mushes over. If I go to the center and look at the center, difficult to control here. All right, what I want to see is that once I go closer to the center here, it's actually getting darker, right? It's bright, it's getting darker as the camera is going closer to it. Why? Again, because things are only calculated here, 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 and here. So I go back to OneNote here. Let's see if we can draw a little image of this. I have a camera here for my eye, and it's looking at this object here. And I have the light somewhere behind me. So if I'm looking at the object here, or let's say here, the direction to me and the direction to the light, this should give a really bright shine spot. But it isn't, because I'm calculating here at the end, where the light is coming from here, I'm coming from here. This is not very close to the normal, the center direction. I'm getting it darker there. Here I have a normal. My eye is here, the light is here, okay, the center is here, it's fairly far from the normal. So I'm never getting this, you know, it's this spot. Here is where the shine spot should be, but I'm never doing a calculation there, right? I'm doing a calculation for this vertex, I'm doing a calculation for this vertex. I'm never doing a calculation for the spot where the light should be brightest. Instead, I calculate a full color here, and then I average them. What could I average instead of averaging the final result? What kind of intermediate result could I store as a varying variable and average between? We're going to do the lighting calculation in the fragment shader. So that means we're going to calculate Phong and Lambert in the fragment shader. But what can I calculate in the vertex shader and have the rasterizer of OpenGL help me by doing the average between them? Sorry? That won't matter really. So kind of the final lights will be done. Let's look at what we do here. We don't even need the ambient for this to work. Even just the diffuse would make a difference, the specularity specifically. So this we're going to calculate in the fragment shader. What about these things? These are kind of the intermediate results. S, V, specifically S and H and the normal. Can we take those vectors and calculate those and then do averages of the vectors? Because the vectors, we don't really have them in the fragment shader. The vectors are per vertex. Does this make sense?
Yeah.
The fact that I want to, let's make a simpler image here. Let's say this is the normal. This is the normal. Here's the eye, which means that the vector V is pointing to the eye here. Or let's just say here's the light. Let's just think about it for diffuse. And the vector V, or the vector S. So this is the vector S, this is the vector S. So instead of calculating the full color here, I calculate the vector S. Instead of calculating the full color, I calculate the vector S, take the normal, and I take the normal. When this is averaged, it'll be this vector, this vector, this vector, this vector, this vector, and the normal will be this, this. So suddenly in the pixels that are here, these averages will kind of converge, and I'll get these vectors that are right next to each other. So the idea with per fragment shading is that we don't do all of the calculations in the fragment shader. We prepare them in the vertex shader, then allow these averages to happen over the vectors. But once we have these vectors averaged, we finish the calculations. We finish the lighting calculations in the fragment shader. Now time's up, so have a nice weekend. But we'll continue this and actually kind of really see interesting things happen. Next lecture, we're going to start throwing lights around, adding the ambient, adding emission, adding things like that, adding motion to the lights.